welcome you for the 16th International Excellent Talks at the Karlsruhe Institute of Technology. Since we started, we already could welcome almost 50 prominent scientists from all over the world for a research day at KIT within this program. And today we are particularly happy to welcome our speaker, Dr. Abel Chuang. He's an associate professor at the School of Engineering at the University of California, Merced, and he's an internationally recognized specialist in fuel cell and electrolysis technologies, which are the key solutions for the future hydrogen energy sustainability. And he holds numerous prestigious awards. His host, Dr. Roswitha Zeiss. Roswitha Zeiss is principal investigator of the Electrochemical Engineering Conversion Group at Helmholtz Institute in Ulm. And she nominated Dr. Chuang for this fellowship. The screen is yours.
Thank you very much for the kind introduction. I had the honor to host Professor Abel Chuang in 2022. And we originally met in 2008 at the Gordon Conference, where he gave a presentation on gas diffusion layers in PEM fuel cells. So it's a long history that we know each other. Right now, he's an associate professor at ucmerced. Location is kind of the central California, the gateway to Yosemite Park. His research focuses on the development of fuel cells and electrolyzer. Specifically, he investigated transport processes in these electrochemical cells, where he's a distinguished expert. He has a very long career, not only an academic long career, but he was also a team leader in General Motors, an industrial lab that really influenced and pushed the fuel cell and research development in the field, and published very essential work in this field. Before he received a PhD at Penn State University and an MBA in Rochester. Originally, he's born in Taiwan. He comes from Taiwan and had a master and a bachelor in aerospace. That's kind of a turn in research in some sense from Taiwan. And I'm really happy for this very fruitful and collaboration, and was such a nice experience. Also, I want to thank you for my group members who really enjoyed your stay and had very nice scientific discussions. So we are looking forward for your talk. The floor is yours, Abel.
I want to thank you for Professor Roth and Professor Zeiss' kind introduction. Today I'm going to use about 40 minutes to run through my background and then my research, and hopefully get that you guys can get to know my research a little bit more. And so I'm going to go through these few topics here. I will have one slide very quickly introduce my background, that kind of connect the dots together, trying to see, okay, why am I doing the type of research I'm doing now? And then for those of you who don't know ucmerced, I have one slide to tell you, as Roswitha said, it's in a central area, which is, you may not be familiar, but it's actually the gateway to Yosemite National Park. So I want to welcome you to come to visit. Then I want to switch gear to talk about hydrogen, talk about fuel cell for automotive application, and some of my initial activities at General Motors. And then I will talk about the type of research that we continue to conduct, and maybe we actually even more expand a little bit at ucmerced. And through that, I will summarize my talk. Very quickly, as Roswitha said, I was actually first in aerospace engineering for my bachelor degree. And during my senior year, I actually started to get involved in rocket propulsion, rocket design. So my master, I actually study a combustion and rocket propulsion for a thruster, which is a 10-pound force monopropellant thruster that controls the altitude of a satellite. And so through that, I started to get really interested in thermal fluids research. Then after that, I spent 2 years working on F-16 technical fighters before I went to Penn State University to work on my doctoral study. And at Penn State, that was really a pivotal research topics because I was working on phase change, two-phase heat transfer device. And through that period of research, I employed a tool called neutron radiography. And that neutron radiography tool is the tool that I can actually see through metal casings and to study two-phase phenomena. It can be evaporation phenomena. It can also be condensation phenomena. And so through the process, I get to know the tools of neutron radiography. I also get to know the principle of two-phase operation in porous media very well. And so right after I finished my doctoral degree, I then stayed behind and to started my career on fuel cell research. And so during that time, I employ the neutron radiography to study, in this case, on the right here, you can see two pictures. So during that time, we had two collaborative projects. On the top, it was with Toyota. On the bottom was with General Motors to study their fuel cell operation and to study their liquid water formation inside the metal casing, which is a single fuel cell. And so we started to understand what there is actually a lot of problems in fuel cell operation when it's related to two-phase flow. And so in 2005, 2004, 2005, then I switched my career to General Motors. I started to work on the application or the research for fuel cell for cars. And until all the way to 2011, then with that knowledge, with that foundation that I have established, I switched gear to become a professor. I first went back to Taiwan to be a professor for 1 year, and then came back to Purdue University before I finally joined ucmerced in 2014. So this is my 9th year here at ucmerced. For those of you who don't know ucmerced, I'll just use one slide to really introduce and hopefully pique your interest to come and visit. It's a 10th UC campus, which was founded in 2005. The newest UC campus. It's located in the center area of California, and like I said, it's actually right next to the Yosemite National Park. And one of our mission is related to triple net zero. And this triple net zero was referring to either energy or environment, involved with net zero energy, net zero landfill waste, and net zero net greenhouse gas emission. And it was because of that mission and because of the overall, focus on energy and environment that attracts me to ucmerced. So I'm going to switch gear a little bit to start talking about hydrogen and fuel cell. And I am assuming not all of you are, some of you are in the area of fuel cell and electrochemistry research like Professor Zeiss, but maybe not all of you are. So I'm going, the talk that I structured today have a bit of overview introduction, but also include a lot of in-depth technical content as well. So I want to very quickly introduce about hydrogen and fuel cell technology. And so if you take a look at from the left to the right, you see a lot of green signs. These are related to hydrogen production, hydrogen delivery, hydrogen storage, and then the end use of hydrogen. And so as I pointed out, my early career was focusing on actually applying transportation. So applying hydrogen in a fuel cell to generate electricity that can be used to power transportation vehicles. And during my time at General Motors, I was mostly focusing on passenger cars. Now I have a little bit more focus on, for example, hydrogen trucks and other different applications. Okay, so I'm going to talk a little bit more about these are the different ways of transportation tools that we have. But my focus in my early years are mostly focusing on passenger cars, and that's the application of the low temperature PEM fuel cell. Okay. So I'm going to very briefly talk about these activities that I did with many of my colleagues at General Motors that really trying to develop fuel cell for passenger cars. And so if you take a look at this engine here, this is literally a fuel cell engine inside housing a fuel cell stack. It has zero emission, zero petroleum because we apply hydrogen, and hopefully this will be green hydrogen. And then if you compare it to the internal combustion engine, it's much more efficient. There's no moving parts, also long range. So it's very efficient. Performance is very well. It can start under cold or hot operating conditions. Right? It can be used for a small passenger size, can also be used for a large SUV or minivans. Has a lot of synergy with renewable energy source. So I have been working on this technology since 2003, 2004. And when we apply a fuel cell in an automotive or for transportation, there are in general 4 different systems. The first system is related to the storage of hydrogen. This is referred to as anode hydrogen storage system. The second system is the fuel cell stack that is responsible for converting hydrogen into electricity. And through the process, because it requires produce heat, so we need a radiator to continuously remove heat away from the fuel cell stack. And also we require oxidizer. So when hydrogen and oxygen combine, it generates heat and water along the process, generate a lot of electricity to drive our power electronics for our powertrain. Right? So that's the overall, this overall, propulsion system can be used for, passenger cars, can be used for trucks, can be used for different type of transportation tools. Okay. A very general and very quick introduction of a fuel cell or low temperature PEM fuel cell. You have the cathode side, which is responsible for reduction reaction. So it's referred to as oxygen reduction. So oxygen combined with proton, electron that produce water. And later on in my talk, I will discuss more in detail why water is actually critical in this situation. On the anode side is where hydrogen is being split into protons and electrons. And through this very carefully designed electrochemical process, we were able to generate electricity. We use this electricity to power cars, power different applications. Okay. And so there are different components inside. Besides the flow, you can see the flow channel that's guiding the oxygen flow or air flow on the cathode side, and then hydrogen flow on the anode side. Within the cell, there are what we refer to as soft goods, which include membrane, electrode, and gas diffusion media. And I'll blow them up to show you what they look like here. Okay. And so if you look inside the center of this fuel cell, you have on the left-hand side is your anode side where hydrogen comes in, diffused through this gas diffusion layer, have hydrogen oxidation reaction at the catalyst layer. Proton would then move through the membrane, be combined with oxygen to generate water. And what's interesting is that if you take a look at this, I show this as a fuel cell transport study. As Professor Zeitz was saying, a lot of my interest was related to transport phenomena, phase change, two-phase transport flow. And so if you take a look at this figure here, there are a lot of many complicated physics. So you have proton transport, you have electron transport, you have hydrogen and oxygen gas transport. Then because fuel cell generate heat, so there's heat transport together. As in order to have very, very good performance, one of the key component is to be able to compress the cell. So in other words, you will be able to enable this electron transport through different layers. So later on, we are going to talk about how important this transport phenomena are refers to in terms for optimizing fuel cell operation or fuel cell durability. And so my first project in General Motors was to be able to study transport media because of my background in terms for two-phase transport in media using neutron radiography. And so when I first studied at General Motors, I was then given the task to study gas diffusion layer, which stands for GDL, and microporous layer, which stands for microporous layer. And I use this to show you the multi-scale transport nature because the gas diffusion layer is actually made of carbon fibers, which has the carbon fiber size is about 7 to 10 micron of each. And when you put them together, stack them up together, the pore size is about 200 micron. Okay. And then if you take a look at this microporous layer, which is a layer on top of this gas diffusion layer, it consists of carbon particles mixed with hydrophobic agents like PTFE. And so if you take a look at this, there are large size, some cracks on top of it, but the pore structure within these carbon particles are roughly about 50 nanometer. So my first task in General Motors was to study, well, what are these material and how can we actually optimize this material to enhance either performance or durability, or to remove issues with generated liquid water. And so the first step that I did was I looked into the process, the design, and the material of this baseline material. So this material is referred to as diffusion media. And so you can take a look at this, start from the PEM precursor to make carbon fiber. And then the type of carbon fiber process to make it as a carbon paper has, in general, two very distinct processes. And I'll talk a little bit about this later on, but at this point, I want you to know that there are two very different processes to make carbon fiber paper. On the left-hand side is mostly through the wet process, which is like the paper making process, referred to as wet laid process. And so you can take a look at them. They are straight fibers, and they have chemical binders. These are carbon binders or resins trying to bind these carbon fiber together. On the right is a very different process. It's called dry lay process. It's actually going through some of the entangling process, mechanical entangling or needle entangling process, to have long fibers that entangle them together through mechanical form. And so the typical difference is on the left is what we refer to as chemical binding. On the right is what we refer to as mechanical binding. And these two different materials or processes will yield material with very different properties. And after this, there are usually graphitization or carbonization to enhance their transport properties. And there's also post-treatment for microporous layer coating or for different form of coating. Right? And so while in General Motors, collected together with my colleagues, we developed different tools to characterize the properties of the gas diffusion layer. One of them is to study electrical transport, both in-plane and through-plane. And then is thermal transport, again, both in-plane thermal transport and then through-plane thermal transport. We were able to also put together a thermal transport model to predict temperature within a fuel cell. We also developed tools that to characterize gas transport in terms for hydrogen transport and oxygen transport. And there was a tool called limiting current that I will introduce a little bit later, that we developed a diagnostic tool to actually characterize the features of hydrogen and oxygen transport within a fuel cell. Last but not least is the mechanical transport. As I said, that the fuel cell requires a strong compression to be able to keep all the cells in good contact and be able to transport heat, transport electricity away from the cell. And so the mechanical property of the diffusion media, which acts as a spring inside the cell, is extremely critical. So we developed tools and developed methods to study different transport of binding of the gas diffusion media, the compressibility of the gas diffusion media, the shear modulus, and develop model to predict when we compress them, what will be the deformation looks like inside the fuel cell. Right? And so those tools were, again, developed with my colleagues at General Motors. Then my second task was then include the microporous layer and electrode on top of the gas diffusion layer. So this is a cross section of a detailed microporous layer, together with the membrane and catalyst layer. And so if you take a look at this, here you have microporous layer, which consists of carbon powder with PTFE. And then you have anode catalyst layer, you have a membrane, and you have a cathode catalyst layer. Then you have another microporous layer, which is a sandwich that's symmetric. So one side will be on the top will be anode side. Hydrogen will flows in and then react here. On the other side will be oxygen side. So oxygen flows in and then react with proton and react with electron to generate water. So water will be generated in this layer. But I want to show you the features of this multi-scale. So you have, different pore size, platinum particles, and different carbon particle size. And then you have this carbon fiber, which is the white stuff here. That's the cross section of the carbon fiber. And then you have large pores on top of it. And so what's interesting about this is, again, transport, very complicated transport issues. So you can see that this microporous layer here, it provides mechanical support for this membrane electrode. So these fibers are not directly contact or damaging these very thin and very flimsy layers. Right? It also shear this MEA from damaging these GDL fibers. And on the left, it provides mechanical support. So you don't have an uniform support or contact of these mechanical properties here. And then it also enhances the uniformity of this layer. So you don't have a lot of voids, a lot of cracks. And again, these scales are relatively small. These are 30 micron scale. So very, very small gaps can actually create puddles, create holes for, to create transport issues. Last but not least is shear electrode from liquid water. So as I mentioned earlier, this layer, which is microporous layer, on the top and bottom, both have strong hydrophobic agent as PTFE. And so this layer is very hydrophobic. So when you have water generated and potentially condensed, water will then be poured out on these large pores rather than these small hydrophobic pores. And so we actually develop a lot of different materials, different tools to characterize and also to study this microporous layer and electrode. And this is what a simple electrode layer looks like. You see there are porous structure. And so you see a very fine, this is now going down to 1 micron. So very small carbon particles carried with this nano-sized platinum particles. And then there is this Nephron or ionomer films. And this interaction and the structure plays a critical role in fuel cell. So we are going to actually talk a little bit about this in my later slides. Okay. The last project before I left General Motors, I worked on different cell architecture. So if you take a look at this, you have membrane and then catalyst layer. And then here you have gas diffusion layer, which has GDL and MPL, which is separated. Right? So this actually have a lot of advantage. Okay, membrane is better protected, but it has poor adhesion between this electrode layer and the microporous layer. And it has also cumbersome roll-to-roll processing steps. So later on, we developed this approach or this cell architecture where you have membrane, but the catalyst layer was then coated directly on the GDL and the microporous layer. So you have this advantage is it improves adhesion. Later on, this will go through hot press. So it becomes a multiple layer structure within a very intimate contact. This process has also advantage for simplified roll-to-roll processing steps for manufacturing. So this was my last project, after I left, before I left General Motors. Along the process, I talk about models and be able to predict transport effects. And then I also involved with these fuel cell models that predict fuel cell performance inside a cell. And this one is referred to as 1D down the channel model, which this is a great tool that captures the physics. And again, I'm going to talk a little bit about this in my later slides. So now switch gear to my fuel cell research at ucmerced, and I should actually correct this. I would refer to as electrochemical research because we did branch out many different type of research areas. And so during my tenure at General Motors, I have the opportunity to experience and to study different scales, going from a very fine catalyst material, integrate them all the way down to a fuel cell stack. So after I left General Motors within my research program, I strategically planned my research activities through these vertically integrated research topics. The first one, which is the most small scale, nanoscale feature, is to synthesize and trying to explore different catalysts that can enhance electrochemical research, enhance electrochemical activity. The second scale is related to the integration of integrating a catalyst nanoparticles into a very high functional electrode layer through the rheological study and then through the integration of the MEA. And the last but not least scale is related to the cell, full cell testing and characterization as well as simulation. So these are 4 different scale research that are vertically integrated. And so you can see that with 1 to 4, level 1 to level 4, it goes from a nanometer scale all the way up to the millimeter scale. Okay, and then if you consider the scale of the channel and the stack, then it can be actually up to centimeter or meter scale. So within this strategic plan, I structure the lab activities around this focus. The first one is material synthesis. The second one is related to material integration or MEA integration. The third approach, the third area is fuel cell experiment. Fourth area, fuel cell diagnostics. Fifth area, fuel cell modeling. And lastly, the system integration. We don't do system integration ourselves at ucmerced, but we rather collaborate with suppliers and vendors to work on system integration. But our research mainly focus on these 5 areas. Okay, material synthesis, integration of catalyst layer or MEA, perform fuel cell experiment diagnostics, and then based on those results, develop fundamental understanding through fuel cell modeling. What I'm going to do in the next 10 slides, I'm going to introduce each area very briefly, but I will not go into detail because these are relatively broad research topics. But rather, instead of going them too deep, I want to introduce them to you. And so you have an idea that what we are doing in the lab, and then maybe through the process, we can have some follow-up discussion to dig deeper within each area. So the first step is, making nanoparticles or making synthesize different, catalysts through different reaction or different activities. And we have different tools for making them. We have hydrothermal tools. We have, flux tools. We have atom fusion tools that we can make material depends on their properties or depends on the precursor. And then after we do that, we perform RDE or RRD evaluation to understanding their fundamental intrinsic properties related to the TEFL slope, related to some of the specific activity of the material through either cyclic voltammetry or through some of the impedance measurement or through some of the performance linear sweep voltammetry analysis. And so this is an illustration of a triple a 3-electrode system. And so through the process, we were able to actually did quite a bit of fundamental research. And we did apply the study for catalyst on all oxygen evolution reaction in alkaline media. Also in acidic media, we studied the role of Nefion and the interaction. And then we also applied some of these tools on nickel carbon-based material to conduct urea oxidation reaction to study the catalytic activity. So we will continue to work in this area to develop catalysts through different type of electrochemical research. The second area is related to MEA design, processing, and integration. And so, as I explained earlier, this is a continuation from my activities or my research at General Motors, how to actually integrate catalysts and make a very highly efficient membrane electrode assembly. And the process starts from selecting materials and then making an ink. So coming up with a different type of ink recipe, and then mix the ink in a homogeneous way, and then applying the ink through a thin film coating, either on a decal or on a gas diffusion layer. And through those, we were be able to integrate them through different architectures. I explained to you earlier that we can either make this as a CCM or a CCDM architecture. They have different advantage and disadvantage within different architecture. Right. So some of these, as you can see here, is a very interesting but very developmental work. So besides some fundamental work, we also did do this developmental ink optimization process. But we actually wanted to instead of just try and error, we want to see if we can actually study the ink to understand their properties and how does the final microstructure of the catalyst layer look like. Right? And so through that, we employ this ink mixing and coating process, which demonstrates here. And then this is referred to as the membrane electroassembly integration. And we can do this with decal transfer, or we can also do this with coating a GDE through the hot press process. So different process that we integrate them. So with that, we were able to then test a full fuel cell to diagnose the properties and the performance of a fuel cell. But as I said, instead of like just doing a try and error, we make a recipe, then we make the MEA, we test the MEA, right? And instead of going from the try and error approach that we make one and then test one knowing if it's good or bad, we actually employ the tool called rheology. So we actually study the rheological behavior of the catalyst ink to study when it is under shear or before shear, what does the microstructure look like? So you can see this is referred to our microporous layer, which has carbon and PTFE. And then on the right here is related to our catalyst ink, which has, platinum carbon typically for low temperature PEM, also have ionomer in there. And so you can see that both of them, if you look at this chart, is a viscosity as a function of shear rate. So both of them exhibit shear thinning behavior. When you have carbon, you have this transition area where there is a little bit of shear thickening, but then it goes to continue to this shear thinning behavior here. Okay, and so we know that this ink is a complex ink that demonstrates shear thinning behavior. But in order to do understanding this a little bit more on microstructure, we also study this dynamic measurement. And within this dynamic measurement, we have a different shear. So 3-step, which is called three-phase rebuild. First step is low shear. Then you shear them at a very high shear rate. You know the viscosity will drop. And then after that, we let the viscosity actually recover itself to understand the time-dependent measurement behavior. Then with this 3-phase rebuild, we were able to study, okay, is the ink actually has thixotropic behavior, or actually this ink on the left, it actually exhibits the rheopathic behavior. And through the study, we were able to understand, okay, we propose different microstructure of, in this case, microporous layer. And so what happened before the intact structure, in other words, before the shear, and then during the shear process, then through the process, we also investigate the primary particles to understand their particle size distribution. And so at the end, after they recover, they actually develop a more stronger behavior in terms for their structure compared to the original behavior. Right? And so this rheological study was able to help us understand potentially what are the structure of the microstructure of these particles, these primary particles. Recently, we expanded this study, not only study for its rheology, but also study for impedance in situ or simultaneously. So we develop and modify our tools to actually implement this real impedance investigation to study the ink, because we know all of our ink has ionic conductivity. Also, it also has electrical conductivity. And through this study, our goal is to understand what are the electrical conductive microstructure look like, and what are potentially the ionic microstructure look like, and then what are their interactions through probing them at different conditions. Right? So these are the tools that we use to study our microporous layer and also study our catalyst layer ink. A few more slides. We just want to show you that we did quite a bit of fuel cell testing and characterization through the fuel cell test station tools that we have. And we also perform fuel cell diagnostics that we continue to establish through the process. And one of the tool is called limiting current study. And I'm going to talk a little bit more about this tool later. And then we also continue to use in situ, water distribution study through neutron radiography. As you can see on the right here, the resolution of the neutron radiography continue to improve. So now instead of seeing water inside the channel, which actually was my study at Penn State University, now we are able to see liquid water inside a very fine pores. Okay, the resolution is down to about 5 micron scale. Okay, so now we can do a little bit more with this tool. We continue to also improve and develop our fuel cell model through this 1D analytical or 1D physics-based model that capture all these interactive transport properties. I'm again going to talk about this a little bit more. And this is an example of a 1D model that shows this different model case and different enhancements through the model to be able to predict or agree better with the experimental data, which is the red dot. On the right here is our circuits for thermal transport. We also have circuits for gas transport, circuits for water transport, and there will be a strong iterative process within these transport models. We also apply this into a 2D or a 3D COMSOL model to use this computational model that study a local distribution. Instead of 1D, this was able to provide a different type of local properties in terms of mechanical properties, in terms of for transport properties, and we were able to study them to understand what are the non-uniformity within the cell. Okay, so we continue to develop these tools within our lab. Last but not least, there are these different types of fuel cell design that we implement and enhance. For example, this is a 3D channel model. So we actually we design and then manufacture this very complicated 3D channel geometry, which looks like a convergent divergent nozzle throughout the whole process. And we were able to perform fuel cell testing and then as well as neutron radiography to validate that its water distribution, to validate its performance, which actually the 3D nozzle here has shown a superior performance of all this conventional design of the flow channel. And so those are basically all the areas of research that we developed or we do at ucmerced. Within the next 5 minutes, I'm going to home in on one of the spotlight research that demonstrate an engineering approach or an approach that we actually solve a very complicated engineering problem through fundamental research. And so I'm going to now zoom in on mostly on the interactive transport within the fuel cell and this whole series of research that we actually have developed. And this actually, the entire research, range more than 10 years of my research time studied within my time at General Motors, all the way even up to today. And so you can see this problem solving loop here. The first step is identify the problem. Then you kind of get a better understanding of the problem, and then you test the idea, right? You test the hypothesis to see if this actually, solving, or is this actually the root cause of the problem? And then you evaluate the results and come back in this loop here. So I just want to use this example to share with you that we have done probably 20, 30, 50 times of this iteration loop throughout this process of solving the interactive transport study in a PEM fuel cell. I feel like that, compared to 10, 15 years ago, we have come a long way. Okay. So what is the problem, right? So I remember that during my time at Penn State University, we collaborate with Toyota and General Motors, and they came to us. That was the time that they were trying to scale up their fuel cell, and so they have to run a higher current density. But they came to us, well, when we run high current density, the performance dropped very quickly. Right? So if you are not familiar with this plot here, on the y-axis is voltage, x-axis is current density. So you want high current density, you want high voltage, a high current density. In other words, you want this line to be as far out and as high as possible. Right? So here I show you two different materials, okay, two different gas diffusion media, to be specific, right? And so you can see that black one actually runs out and then drop down very quickly at the current density of about 1.7. On the red one, it can run at a higher current density. Okay, I'm not saying that the material wise, the red one is better than the black one. I'm using this example to demonstrate the physics of the study, because depends on different operating conditions. I can, for example, on the left-hand side, you can see the black one is better than the red one. But when you go into this operating condition, which is have a little bit more highly humidified case, then you can see that the red one is now much better than the black one. We observe this problem, and we want to make the black one to run as far out as possible, right? So I show you this feature before, like this is the MEA. So you have MEA in the middle, and these two material, one is Torre, one is Freudenberg. This refers to the GDL on the transport layer here. Okay, I plot this, if you remember, I plot this not in scale, right? Because the MEA, which is membrane and electrode, the entire thickness is usually about 20 micron, very, very thin. But this transport gas diffusion media, gas diffusion layer, that thickness is at least 10 times thicker, about 200 micron. So a lot of the transport issues happens actually inside the gas diffusion layer. During that time, we have a few questions. We were wondering why there is high concentration loss. There's a high loss here at high current density. So when we go up to higher and higher current density, this loss show up very quickly. We are wondering why this happened. And this only happens for some material, but not for other material. The second question is that, are there liquid water condensation inside the cell? Is that the root cause of the problem, right? And we have already established the answer for that early on, okay? But then a little bit more fundamental question is, where is the liquid water? Okay, and then what are the governing parameters for this flooding behavior or for this flooding phenomena? What can we do to either prevent this from happening or mitigate them, right? This will be either material solution or engineering design solution. So we have this series of problems that we identify. And these are the steps. I'm going to list 7 steps that we did. Again, at the very beginning, these steps are collaborative work with my colleagues at General Motors. And then later on, we continue to develop them within our lab at ucmerced. The first step is that we identify and fabricate materials with extreme properties. Okay, and remember I show you this. There are 2 different ways that we can produce this gas diffusion layer. On the left-hand side is the wet lay process. On the right-hand side is the dry lay process. And what's interesting is that for the wet lay process on the left-hand side, because it has this chemical resin, in order to be able to carbonize this chemical resin, this material usually are graphitized at a much higher temperature. It's roughly about 2000 degrees C. Some of them can be as high as 2400 degrees Celsius. In fact, in this case, because we want to study extreme properties, so we actually collaborate with companies to make this material. That was when I was at General Motors. We actually make this material to have very high carbonization temperature. On the right-hand side is the Freudenberg material, which is produced, manufactured by this dry lay process. So there is no resin, as you can see, there's just fibers. Maybe there's a little bit of filler, but mostly fibers, and they are mechanically entangled. Right? So both of them has very different properties, very different features. we identify them because we know with these properties, we have a better idea to maximize the signal that we study. The different step, the second step is that we develop an in situ or in operando tools to characterize transport resistance. And this is referred to as limiting current process. Okay. This was at first developed by General Motors. As you can see here, we actually change our concentration of oxygen. We can also change the concentration of hydrogen and identify what is the transport resistance of this gas diffusion layer, which refers to this R, which is resistance. In this case, is oxygen. Of course, we can also study hydrogen, and you can see this R. And so we measure this limiting current, which is the dot in the center, and we control the concentration. As you can see, when you double the concentration, your limiting current also doubled. So you go from 0.5 to 1, 1 to 2, 2 to 4. You can see that this limiting current double as a function of concentration. So you know that the resistance of these materials is a constant. So we know that we developed this tool. This tool is very useful in characterizing transport properties. So apply them in a real cell. Step 3, we identify the transport limitation. So we apply the tools on this material that has toroid material. On the x-axis here, now you have this on the on the y-axis is the transport resistance. So this is oxygen transport resistance. So as you can see, this resistance is actually not a constant. There will be when the current density increase, the transport also increase. This is a sign of liquid water condensation. And so if you take a look at this on the Frauenberg, which actually doesn't show a drastic transition or a dramatic increase compared to the one on the left. So we observe this fundamental difference. We develop the tool, characterize this material, and then find out that these actually have very different behavior, which is actually responsible for the difference of this performance. Because for the toroid, you can see that at high current density, you have very high oxygen transport resistance, right? And low current density is good, but high is bad. That's why you see this very dramatic drop of the performance. On the other hand, for Frauenberg, you can see that the increase of the transport resistance is not so high. So it continues to be able to run at a high current density. And we also identified that this happens on the cathode side. So we know that this is from the oxygen transport limitation. So once we know that, we know the physics, what we wanted to do is we want to establish the tool, develop a tool that can actually characterize this liquid water, identify its location, identify its distribution. So we developed this. We actually make this cell. This was done at when I was at ucmerced, and so we developed the tool. We put it into the neutron radiography to characterize its water transport. And so, as I said, this tool now is capable of identifying liquid water in a very fine scale. So we were able to look at, both toroid and Frauenberg material. This case is a low current density. And you can see the blue means it's liquid water. Black means there's no liquid water. So you can see the MEA membrane has a little bit of water, but the anode and the cathode gas diffusion media for both of them do not have liquid water. But when we increase the current density, you can very quickly see that for the toroid material, again, anode diffusion media is no problem. It's relatively dry. Okay, but on the cathode, again, the cathode is on the bottom side. Okay, so the cathode diffusion media, you can see it's pretty much filled with liquid water everywhere. But for Frauenberg material, the cathode diffusion media, you can see there's some water here, but no water here. Some water here, no water here. And this actually corresponding to the compression length and the channel. So oxygen is fed in the channel. So this actually have no problem for oxygen to actually diffuse into this catalyst layer. But for the toroid material, you can see that it has this layer is all wet, and you can also see that this water is existed within the entire layer. But for Frauenberg, you can see the distribution of water is very different. So it shows that Torre shows flooding on the cathode diffusion media throughout, but Frauenberg shows only a limited area. Okay, and so this observation agrees perfectly with our characterization tool through the transport study. Okay. Now the fifth step is to develop the fundamental understanding of the feature. So we actually look into the physics of heat transport and then gas transport. I'm not going to go through this in detail. We actually published all this work, so you can, if you're interested, feel free to look into them. But I'm going to share with you that because of their thermal conductivity and because their transport property, there are two different phenomena. Frauenberg looks like the blue line, where the saturated pressure, which is the dotted line, is almost always above the water vapor pressure, right? And so there will be no condensation, but there will be initiate of condensation on the right-hand side, okay, which is away from the catalyst layer. But for the red, which is Torre, it's the opposite. You have this saturated pressure that's here on the dotted line, but the water pressure is the solid red line. And you can see when the water pressure is above the saturation pressure, you will start to condense. And it condenses very quickly on the catalyst layer, right, near the catalyst layer side. And so once we develop this fundamental understanding, we identify governing properties of the gas diffusion layer. And these are thermal conductivity and gas diffusivity. Thermal conductivity is K. Gas diffusivity can be represented as tortuosity divided by porosity, right? So you can see different material like Torre is red. Their sum is actually 5.75. Like Frauenberg, their product is 5.7. The product of this is 0.42. So there is a dramatic difference. These are the governing properties or parameters of the GDL. The last step is based on this fundamental understanding and physical analysis, we develop a fuel cell two-phase model, which we refer to as this tendril model here. So when liquid water starts to condense, it starts to form this water tendril. And when the water tendril forms, the transport property will increase. And based on this physics of the tendril model, we were able to predict. The black line is model prediction. The symbols are experimental measurement. So we were able to predict this transition from dry to the wet in the gas diffusion media. And then we were able to go from the dry model, which is the red line, to the black line, which is the wet model. The symbols are experimental data. So you can see that we still fail to predict this transition here. But with that, we perform a lot of experiments to develop an empirical correlation for the electroflooding model. And after we implement this two-phase electroflooding model, we were able now to predict this performance well. Okay, so through this 7-step, my goal is to demonstrate that within this process, even though it's more, it actually ranged for more than 10 years, but through this process, we were able to solve develop fundamental understanding and solve the problems, identify the governing material properties, and then based on those understanding, actually design future materials that can enhance our performance in a fuel cell. So I'm going to wrap up my talk here very quick. Now, hydrogen at scale is a big, research topic. Hydrogen economy is big, so there are a lot of development in this area. And within that, our lab in the past 5 years has expanded our research scope. The fundamentals is still based on transport, based on material, based on electrochemical, or based on electrochemistry. But we expanded into a PEM electrolysis cell to actually generate hydrogen by splitting water. We also expanded into alkaline fuel cell and alkaline electrolysis cell. We also expanded to solid oxide fuel cell study, and we also lastly expanded to CO2 electrolysis cell. What I'm going to point out is that all the physics in terms of electrochemistry, transport, these properties are very, very similar to the PEM fuel cell that we developed a very strong, significant fundamental understanding. right? So we apply those basic principles, basic problem-solving strategies to try to expand our research in this area. Okay. Before I conclude my talk, I want to thank my team members here. They work very hard to be able to accomplish this research results, and also my alumni. Okay, with that, I'm going to conclude my talk with this summary. So we at ucmerced are dedicated to develop renewable energy. We develop strong expertise in fuel cell, water or CO2 electrolysis characterization, diagnostics, and modeling. Lastly, we want to welcome any research and educational collaboration to identify problems or discover solutions through fundamental research for electrochemical study. With that, I conclude my talk. I want to thank you for your attention. Thank you for your time.
Thank you, Abel, for your talk. Very interesting one. It seems like a very broad topic. We are now ready to open up for the questions.
Thank you so much for the question. I wanted to point out to one of the characterization tools that we developed, and we actually recently also published that work as well. So if you take a look at these features, this is the characterization for, in this case, the porous media before and after liquid water saturation. This material that we structure here is specially designed that has hydrophobic properties. Sorry, I didn't capture the name, but as the engineer from or researcher from DSW was mentioning, that hydrophobicity in this cell actually has a significant impact. One of our studies shows that if we have different level of hydrophobicity, or even have no hydrophobicity, these transport properties actually do not reach plateau. I can show you this transition here. These are the material. You can see that it actually from dry to wet and reach a plateau. If you have low level of hydrophobicity, or if you remove your micropores there, this transition will actually shoot up all the way rather than reaching a plateau. So yes, indeed, hydrophobicity is a critical factors in determining the liquid water condensation and determining the fuel cell performance in this case. Thank you so much, Professor. This material, so when we manufacture this, the feature that you see here, ranging between about 330 micron to about 660 micron.
Mm-hmm.
We use a resin impregnated graphite plate, and we actually use the milling, process, machining process to do this. Okay, but you ask a critical problem, also a critical question. Right now we have an active project on additive manufacturing for 3D printing for lithography to actually design a pattern feature to be able to control transport properties. And so this is something that we are actively doing now. We don't have a significant results in this area, but this is an area that we are actively pursuing. The reason we actually expanded ourselves into the alkaline environment is because in alkaline media, oxygen reduction or oxygen evolution is easier to apply non-noble catalysts, as in this case, as Professor David Nevitt was saying, for non-precious metal, it's much easier to apply in alkaline media. So we actually apply this in alkaline oxygen evolution and also in alkaline oxygen reduction reaction. Some of actually the catalysts that we developed for this nickel-based material, we also apply them into a hydrogen evolution study. So we also have some preliminary results for that. So if you're interested, we can certainly share those results with you later after this presentation. When we run these two materials through a long life durability protocol testing for say 1,000 hours or 5,000 hours, does this trend continue, right? My honest and short answer is that we actually did not run both of them to long durability, but because again, these two materials are actually for research purpose. We kind of special design them for their properties. But for the material that we put in the fuel cell stack to run the abilities, those materials are typically very robust in terms of their performance under both dry and wet condition. And the failure mode that we observe are either through membrane degradation, either chemical degradation or membrane pinholes that we observe, or catalyst degradation. It's like loss of ECSA, loss of its activity, or actually platinum dissolution, carbon corrosion. These are more of a significant issue in durability study rather than the diffusion media, because like I said, we don't purposely put a diffusion media that will cause flooding and then run durability test. Having said that, I mentioned a little bit earlier today that we are working on developing fuel cells for hydrogen trucks. And then for hydrogen trucks, these durability issues are critical. And so the focus is more, again, the focus is more on membrane, mechanical and chemical durability, and then the catalyst layer degradation. Even though for the truck, we were able to afford higher platinum loading, but still the platinum degradation is an issue. Based on my experience, the level of degradation, we saw what we did previously was, again, this was whenever the General Motors, we have a long durability fuel cell stack, and we evaluate the performance for the gas diffusion layer itself. And then after the durability stack, we actually disassemble the cell, separate the gas diffusion layer and the MEA, and characterize their degradation individually. Of course, there would be some non-ideal situation, because now you kind of eliminate your microporous layer and your catalyst layer. But based on our study for gas diffusion layer, not microporous layer, but gas diffusion layer, the performance is still relatively good. It degrades a little bit. But okay, when I said degradation, usually you can see that if you take a look at this chart, the onset of flooding and the level of flooding increased, but the trend still remains pretty good. Having said that, our ECSA loss and our membrane thinning are much more severe at that time. So that would be my experience. I don't know if there are other experts in this area can comment on this. And on top of that, what's even more complicated is actually there will be local transport resistance, which is in the catalyst layer, which is referred to as related to flooding as well, which we actually observed. And that was the work that we did on this this level of study, which different catalyst utilization, which is actually responsible for flooding as well, more related to the catalyst layer. And so yes, you are absolutely correct. Before we get rid of PTFE, we probably have to find ways to modify our Nephium, because Nephium is modified PTFE and it's right next to the catalyst layer. And so that is much more worrisome. PTFE inside the gas diffusion layer and microporous layer are a little bit farther away from the platinum carbon. And so potentially they are not as detrimental, but the Nephium structure, PTFE structure, the phosphoric acid, fluorine, these are right inside the catalyst layer, probably has something that probably we need to find ways to mitigate first or modify first. If you have someone in the audience that's more material oriented, that you can modify carbon fiber and try to actually implement some various of hydrophobicity, I think that would be an innovation. Yeah.
Thank you once again for Abel for this talk. Thank you for everyone for being with us today. Yes, Abel, it was nice to host you here at KIT during your 2 visits. I see that your cooperation is going on, so maybe there will be an opportunity to meet you in Karlsruhe once again.
Thank you so much, Alina, and thank you, Professor Rose, for having for KIT and Roswitha to help me. I hope that this collaboration will definitely continue. I'm certainly collaborating with Professor Zeiss, and I hope that this collaboration will continue. Yeah.
So
Thank you for being with us.
Very
All
much.
the best.
Thank you. Okay.
Bye bye.
Okay. Bye. Bye. Cheers. Auf Wiedersehen.